He's probably. Oh, he's already been here. I've been here like 10 minutes.
Me and Marvin Paul. Come on right now. Come on right now.
You're good. You want to kiss it? No, guys.
All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? We're good. Have a good weekend. I see. I see. Well, it's another week of the week in paradise again. I know how it is. Okay, so this week, so we have another set of biomechanics to go over this week. So this week we're going over lower extremity. So we'll be kind of talking about that throughout the whole week. But I think probably the thing that's on everyone's mind, or if it wasn't, it probably is now, is the midterm exam. So our first midterm exam is planned for next Wednesday. So that's what we're looking forward to. So that's what we did in class. So just as a reminder, the midterm exam will only be administered in person. And so if you are on Zoom right now, please make plans to come to the campus on Wednesday. So the vast majority of the course, I don't mind if you're at home or if you're in your car or whatever, watching the lecture, but for the midterm exam, I do have to have everyone here. And that's just just for fairness. Okay. And so it's going to be a 75-minute exam. It's going to take place during the lecture, and then once the lecture is done. Okay. All right, so some information about the exam. And so the format of the exam, you follow my kind of usual format. And so if you've had me as an instructor before, this should be nothing new. So there are going to be 4 short answer conceptual questions. So that's going to be worth 40% of the points. And then I have 3 kind of problem solving type questions. And for this class, the only types of problems that we've really solved just occurred, in the last 2 weeks, have been kind of static analysis type problems. So all 3 of those problems are going to be the same in terms of what you're going to find out. And so in all of those 3 problems, you're going to be solving with the muscle force, solving with the joint reaction forces. And so you're going to be, doing a free body diagram with force balance, moment balances, and so. Basically the same as what you did in the last homework and what you're going to do for this upcoming homework as well. Okay. In terms of what you can bring to the exam, so you can bring 1 sheet of notes, and so the sheet of notes is 8.5 by 11, a size paper. You can write on both sides. You can write it. You can type it. You can take all the lecture notes and then make it like super small and then print it on your paper if you really want. That's not helpful. I've seen someone that tried that and he was not successful. So you're welcome to try, but generally what I recommend for students is that you kind of write your own cheat sheet. And so think of it as kind of like almost like a summary of all the notes that we've written so far. Okay. And that's usually kind of what's most effective. So I have the cheat sheet there just because in writing the cheat sheet, kind of what you have to do is you have to kind of synthesize everything that we've learned so far. And in doing so, that's actually a great study tool by itself. So, making that cheat sheet, of course, is going to help you on the exam, just to have it as a resource, but writing it is also a great form of study. So definitely, put some thought into your cheat sheet and actually use it as part of your studying. And I think you'll find that it's, both more effective for you during the exam and effective just as a good study. Okay. Of course, you can bring your writing utensil, so pencil, pen, whatever you feel most comfortable with, and a calculator. Okay, the calculator is just there to kind of help you with calculations, but just so you don't get bogged down with any kind of long multiplication or division. All right, and so to give you some additional practice for the exam, I did post a homework just about an hour ago. So that's homework 3. And so the primary purpose of homework 3 is to give you more practice doing these static biomechanical problems, right? And so there are just three conceptual questions and then 3 kind of a little bit more lengthy kind of problems, right? So that'll be due a week from today. So that's due on Monday, October 2nd by 11:59 p.m. Okay. And so by that time, right after the due date for that homework, I am going to post the solutions to that homework, so you have that as well. Okay. And then the solutions for homework 2 will be posted as soon as I finish grading that, which probably be sometime in the middle of this week. Okay. In addition to those, I've also posted a study guide. And so if you look on the weekly page for week 6, at the bottom there, you should see a new document that was just posted about an hour ago, which is a study guide for the mini. Okay, so definitely look at the study guide. And so I think for this class in particular, we've gone over a lot of conceptual information. And so the study guide is mostly there to help you kind of organize all that conceptual information kind of into one place so that you kind of know what to expect in terms of that. All right. So exam next week. Take a look at the study guide and in terms of practice for the problem solving portion, I always tell my students that looking at the homeworks again and redoing the homework problems is probably your best resource. But I did get some requests to post some additional problems. So what I'm going to do is I'm going to post the midterm exam that I gave last year for the class as an additional resource, and then I'll do my best to try to find some additional problems to post as well. So for those additional problems, I'm probably not going to have worked out solutions for them, but I'll put them there just so that you can just have some more practice. Okay. All right. So lots of announcements today. Are there any questions on any of this before we get started? Yes.
Are you gonna have the solutions to those extra problems on it?
So for the
Answer?
previous midterm, I will have worked out solutions for those. But for the extra problems, I'll try to find ones with just the solutions to it. I'm probably not going to work it out all the way, but I'll at least give you the. Yeah, cool. Yeah, I'll look through some of the other textbooks there. All right, any other questions on the midterm or anything that's coming up over the next couple of weeks? Okay, all right, so let's go and get started. And so the topic for this week is lower extremity biomechanics. So, the format of the lecture this week is going to follow pretty much exactly what we did last week with upper extremity, except, we're going over a different part of the body. Okay, so first let's talk about kind of the general characteristics of the lower extremity. And so when we talk about the lower extremity, what I mean is the lower part of your body. So that consists of your hip, your legs, your ankle, and your foot. Okay, and so when we talk about the primary responsibilities of the lower extremity, there are 2. In fact, these 2 responsibilities are actually quite different in terms of what they require. And so on the one hand, your lower extremity, its main function is to support the weight of your body, and so I call that weight bearing. And so for that reason, your lower extremity has to be very strong, has to be very robust. Okay, but it's also responsible for locomotion. So what that means is that it's responsible for getting you from point A to point B. Okay, so whenever you walk somewhere, whenever you run somewhere, even when you're using a device like a bike or a scooter or a skateboard or something. Your lower extremity is involved in a heavy kind of way. So, and so it kind of puts it in kind of 2 extremes. And so on the one hand, it has to be strong and robust to support your weight, without any issues and without any problems. But it also has to be flexible enough in order to, give your body enough locomotion. Especially if you're an athlete or if you're someone that likes to play sports or move your body a lot, right? Then it's really important that your lower body be able to support all of those motions. Okay. And so when you compare it to the upper extremity, your lower extremity is has a lower range of motion. Okay, so it's not as flexible and more importantly, it's not as delicate as your upper extremity. Okay, even though you have your feet, your feet aren't as capable as your hands to do some of the more delicate tasks like writing or or play an instrument or things like that. Okay. But it sacrifices some of that flexibility to give it strength. Okay? And in your lower extremity, you have some of the most stable joints in your body. So the hip being the most stable joint, but your knee and ankle are actually not too bad too compared to other parts of your body. Right? Your lower body has some of the largest muscles in your body, and so the muscles in your leg, your quadricep muscles, your hamstring muscles, your calf muscles are some of the strongest in your body because it's again it's responsible for locomotion. Okay, your sense of balance a lot has to do with kind of how powerful your lower extremity is. So it's a very interesting part of the body because again like you have kind of these two extremes kind of going on, and they both kind of have to be satisfied by your lower extremity. Okay. And so if you're talking purely from an engineering point of view, the design requirements for the lower extremity are probably the most extreme out of every part of your body. All right, so let's take a look at the bones for the lower extremity. Okay. And so here are the list of all the major bones, at least the ones that we'll talk about in the class. Okay. And so we start with the pelvic bone, and so that's the bone that's in your pelvis. Okay. And so when I say the pelvic bone, it's really a collection of 3 different bones. So we have the hip bone, we have sacrum, and the coccyx, which is your tailbone. Okay. And kind of the most probably defining characteristic of the pelvic bone is the very deep kind of spherical cavity where your thigh bone kind of interacts with, called the acetabulum, which is kind of you have one on both sides, one for each of your femurs. And then going from the pelvic bone, going downwards, going to the inferior direction, we have the femur. And so the femur is it's the largest long bone in your body, and it provides a lot of structural stability to your thigh. Okay, and again, the most defining characteristic of the femur is its head, and so the femoral head kind of inserts into this acetabulum kind of right here, and forms what we know as the hip joint, which is one of the most stable joints in the body. Okay. All right, and so going downwards, we then move on to the patella. So the patella is your kneecap bone, okay? And so it's almost like kind of like a flat bone that kind of protects the front side of your knee. Okay? And so the primary purpose of the patella is that generally as you kind of walk around, and move around, the front of your knee kind of bangs into stuff a little bit because the way most people walk, they kind of lead with their knees a bit. And so the patella is there to kind of protect the bones and protect the soft tissue below there. Okay. And then going downward, we have the tibia. So the tibia is the larger of the 2 bones in your lower leg. And so it's located kind of in the front and provides kind of the larger articulating surfaces for the knee and ankle. And then you have the fibula, which is in the back of the lower leg, and provides kind of more support in the lateral. Okay. Then when you go down to your feet, you have the tarsals, and so the tarsals are the main bones in your feet. And so very similar to the hand, your feet are actually comprised of lots of little tiny bones that are all kind of interconnected by joints. And so your feet has a decent amount of flexibility, not as much as your hand, but a decent amount. And then we have the metatarsals, which are the bones in your toes. All right, so that's just kind of a very quick overview of the major bones. Of course, it's not every single bone, and so all the individual tarsals and all the individual metatarsals have their own name. But just for our purposes, this will be such. Any questions on this? Okay, so now let's look at the joints of the lower extremity. So we have 3 main joints, and so we have the hip joint. We've talked about the hip joint a lot in this class, and so it's the most stable joint in the body. Yet it still has a very large range of motion, considering how stable it is. And so it's made of small socket joints, and so very similar to the shoulder, but it does not have as large a range of motion as the shoulder, but still quite impressive for kind of how stable it is. Okay. All right, then we have the knee joint. So the knee joint is the joint between your upper leg and your lower leg. And the knee joint is quite fascinating in the sense that it relies on ligaments much more than any other joint in your body in order to stabilize it. So we talked, I think, very briefly about the ligaments in the knee before, but we'll talk about it a bit more this week as well. Okay. And then finally, we have the ankle joint at the very bottom of your body. So the ankle joint is very interesting because it's again like very similar to the knee joint. The bones that actually make up the ankle joint don't actually fit all that well together. And so it relies a lot on the muscles in your lower leg as well as the ligaments and the tendons for its stability. But actually, you know, because of how much weight gets put on the ankle joint and because of, you know, just the way that people kind of twist their ankles a lot, ankle injuries are probably one of the most common types of injuries that you can have in your body, at least in terms of sprains, in terms of kind of soft tissue damage. And so we'll talk a bit more about that. Okay. Let's talk a bit more about the ligaments in the knees because these actually come up quite a bit. And so knee injuries are very common in people. Okay. My father, you know, I think I might have mentioned before, he tore his ACL playing basketball when he was in his kind of mid-40s, and he said he's since had surgery to replace it, but he's kind of hasn't been the same since then. So you know, it's a big issue. Okay. And so there are four main ligaments in the knee, and they come in kind of groups of two. And so the first group of ligaments are the ACL and the PCL. So these are the cruciate ligaments. Okay. And the ACL and PCL kind of are responsible for preventing any kind of forward and backward sliding motion of the knee. Okay. And they're given this name cruciate because if you kind of look at their pattern here, they almost form a cross on the inside of your knee. Okay. And so among these two ligaments, the ACL is the one that's more commonly injured. And so when your ACL is injured, you know, it kind of makes it very easy for your lower leg to kind of slide forward relative to your upper leg. That can cause a lot of issues. Okay, and then we have the two collateral ligaments, and so we have the MCL. So the MCL is the medial collateral ligament, and the LCL, which is lateral collateral. The medial MCL, that one, inside of your body. So you kind of feel kind of the inside surface of your knee. That's where the MCL is. Okay. Whereas the LCL is on the outside. And among these two, there's one ligament here that's more than the MCL. Okay. In fact, you know, if you follow the NFL, there's the football player that just injured or just ruptured the MCL. He plays for the Cleveland Browns. His name's Nick Chubb. He's on my fantasy team. So I'm kind of screwed now, but it's okay. He's having a much worse time now. So. And the reason the MCL is much more injured is that, you know, in order for your LCL to get injured, when your whole leg kind of has to bend kind of interior like this, because you want to stretch kind of that outside. And because of the flexibility of the hip joint, you know, the hip joint can actually take a lot of that rotation, whereas you don't actually have a lot of rotation kind of towards the outside. When you kind of your knees buckle and your knee kind of bends inwards, you know, that puts a lot of stress on the MCL, which causes it to get injured. Okay. Not to say that it's impossible. So it is possible to injure your LCL. It's just very uncommon relative to the MCL. Okay. Okay. And so those are the four ligaments in the knee. And so in the back of your leg, you know, kind of closer to your heel, you have this very crucial tendon in your body. So if you recall, you know, tendons are the soft tissues in your body that attach your muscles to your bones. And so we have the tendon in the back called your Achilles tendon, which attaches your calf muscle to your foot base. Okay. And it's a very crucial tendon because if you rupture this tendon or if you injure it, then your calf muscle is not able to basically act on the foot, you know. And so you basically kind of lose all kind of mobility in that. This is also another common injury for athletes, and so you know, if you rupture your Achilles, then that's usually a pretty bad thing. You're going to be out for a while. Okay. All right, and the last piece of soft tissue in the knee that we'll talk about is the meniscus. And so even though you know you have two menisci here, the lateral and the medial menisci, you know, I kind of just group them together because they both kind of serve the same purpose, and they're almost kind of like a soft kind of cushion in between kind of the femur and the tibia. And so, you know, naturally, you know, as you walk and as you kind of go about your day, kind of your bones and your lower legs kind of bang against each other. And so the meniscus is there to kind of soften that and cushion that, and to help prevent getting arthritis or any kind of joint disease. Okay. All right. Any questions on this so far? Okay. Okay. So let's talk about the muscles. And so we'll be talking about these a lot as we go through our static analysis. So these are the main muscles in the lower body, and so we have the two muscles in your butt, and so we have the gluteus maximus and the gluteus medius. Okay, and so they're very close to each other, and so they're both kind of make up muscles in your butt. Okay, and so the gluteus maximus, its main function is to allow for hip extension. Okay. The gluteus medius is there for hip abduction. So remember, abduction is kind of movement away from your body. Okay. Next, we have the quadricep muscles. So the quadricep muscles are the muscles in front of your thighs. Okay. And so this is mostly responsible for knee extension and hip flexion. Okay. Next, we have the hamstring muscles. So the hamstring muscles are kind of on the back of your thigh. So the hamstrings actually refers to quite a few, actually several muscles that are back there. So you can see kind of the some of the muscles here. So we have the biceps femoris, the semitendinosus, and the semimembranosus. Okay, but we kind of just group them all together as hamstrings because they all kind of serve the same purpose. And those are responsible for knee flexion and hip extension. And then finally we have the calf muscles. And very similar to the very similar to the hamstrings, your calf is made up of several different muscles. And so we have the gastrocnemius, we have the perineal muscle group here, which is again a group of muscles, and we have the soleus muscle, which is kind of hidden underneath this. And so those are mostly responsible for plantar flexion of your under. And if you're curious where the Achilles tendon is, the Achilles tendon is this kind of gigantic tendon that we have kind of right here. And so you can see it's a very much bigger than a lot of the other tendons in your body. And so once that gets ruptured, then you're kind of in trouble. You're not going to be moving for a long time. Okay. Any questions on the muscles? I believe this is it before we jump into the calculations. Okay. Yeah. Okay. So we'll talk about injuries later. So let me go ahead and swap to the iPad. Okay. And so for the rest of class today, and and for the majority of class on Wednesday, we're going to be doing just example problems, for the lower hip. Okay, so we're going to start with the hip. So we're going to do a couple of examples on the hip first, just because a lot of people just end up having the hip problems. Okay, so let's first kind of take a look at a healthy hip. So let's kind of see how that works. Okay. And so I'm looking primarily at kind of the side of the hip right here. Okay. So this is a muscle that we don't really think about a lot, but it's actually used a lot throughout your day. It's just you don't really realize. Okay. And so I'm gonna do this one a little bit differently. So just because it's a bit more relevant here, I am going to draw the bones. Okay. I'm going to draw the pelvic bone. And we're gonna have a femur that comes in here. This right here, femur, pelvic bone. Okay. And the muscle that we're going to be looking at is going to be attached kind of right above the pelvic bone, right onto the right above the femur, and right onto the pelvic. So we have FM just like this. Okay. This angle here, so this angle here is 70 degrees. So that's going to be one of your gluteus maximus muscles. So one of your gluteus maximus muscle kind of wraps around a little bit and attaches there. Okay. And then as the gluteus maximus muscle kind of contracts, it of course is going to kind of force the femur into itself. So it's going to be a stabilizing force. Okay. And so to counteract this, we're also going to have a joint reaction force acting in this direction. And then actually, you know, for this particular case, this is going to be a little bit different than our usual examples. I'm going to give you the direction of the joint reaction force. Okay. And so that's going to be the J force that's acting in that direction. Okay. One more force that I'm going to apply here, and it's going to be a remote force, and I'm going to apply the force of the person's body. Okay. So remember, you know, the lower body is primarily responsible for weight bearing. Okay, and so whenever you do any kind of, you know, for most cases, when you do kind of static analysis of the lower body, the weight is going to play a big factor. Okay, and so for this case, I'm going to apply the weight kind of closer to kind of the midline of the body over here. The WT here is the weight. Okay. All right, so that's what we're working with in this problem. Okay. All right, so from this example, just like we normally do, we're gonna compute the magnitude of the muscle force. And also the joint reaction force. But unlike all the problems we had last week here, we actually know the direction of the joint reaction force beforehand, right? And so we already know that it acts with an angle of 75 degrees relative to the horizontal. Okay. And so since we already know that direction, we don't have to split up the joint reaction force into Jx and Jy like we did before. So in this case, we're only solving for the magnitude of the joint reaction force vector. Okay. And so unlike all the problems we did last week, we actually only have two unknowns in this case. And so with that in mind, you know, we're only going to need two equations to solve the system. Okay. And since, you know, we're not given any distances in this problem, you know, I didn't give you kind of the attachment distance, or I didn't tell you kind of you know, the geometry of the joint or where the weight's acting. What's going to be most convenient is actually to do just the sum of forces. Sum of forces in the x direction, sum of forces in the y direction. If we only have two unknowns, you know, we only need those two equations to solve this. All right, any questions on the setup of the problem? Okay. All right, before we actually go about solving it, let me give you a little bit more context in terms of, you know, what we're actually computing. Okay. So this situation, you know, where you have your hip abductors kind of supporting, you know, basically helping to support the weight, this happened basically every time you take a step. Okay. And so I want you to kind of observe this next time, you know, probably maybe after the class. just kind of, you're going to see kind of people walking around the quad, kind of watch and see kind of how they walk, right? And so, your body is a weight that needs to be supported by your legs, right? When you're standing on two legs, you have kind of both your legs there to kind of support your weight, kind of keep you balanced, right? But when you walk, there's a period of time when one foot is off the ground, right? And that's what happens when you take a step. And so if you kind of watch people carefully, if you kind of watch the way they walk, when they take a step and they lift one leg off the ground, what you'll notice is that they'll kind of shift their weight in a way such that their center of gravity is right on top of their foot. Do my best to kind of do this with kind of a stick figure here. Let's say this person is walking. Let me do it with the let me just draw the way. All right, and so when a person's walking, what you'll notice is that their leg is going to be kind of like this. So that when the person's center of gravity, so imagine right here being the pelvic bone. Here being ground. Okay. There's a point in your walking cycle where your center of gravity is going to be right above there. Okay. So that you're perfectly balanced, right? Because if you had a situation where your center of gravity was off, right, and so you can kind of see kind of where I am now, right, and so when I'm standing on one leg, the natural thing for me to do is to try to kind of balance my center of gravity right over my foot. But when I try to kind of lean to one side, right, I very quickly kind of fall over because your center of gravity is not right on top of you. Okay. So that's fine. So that's great. And so if we didn't do that, people will be just kind of falling all over the place, walking, and that would cause all. But by doing so, and I kind of exaggerated kind of the bend here. By doing so, by kind of putting your foot into this position, you actually put a lot of stress onto that muscle that's kind of right on the side of your body. Okay. Okay. Because if you kind of look at the leg under this way, right? And so if you assume that your foot is kind of firmly planted, so your foot is kind of fixed onto the ground, right? You kind of almost have like a leaning tower of Pisa here, where what the leg kind of wants to do, right? When you kind of lean that way, is the leg kind of wants to kind of continue falling over and kind of rotate down like that. Right? That's what the leg wants to do. That's kind of what gravity kind of wants it to do, and kind of the momentum of your body wants it to do as well. Okay. But what prevents that from happening, what kind of keeps your leg kind of attached to your hip, are the muscles at your hip. And so in other words, your hip abductors. Okay. And so when someone says they have a bad hip or they have kind of an injured hip, usually it's their hip abductors, and that usually what makes it kind of difficult for them. Okay. And so for this example, we're going to look at a healthy hip, and so we're going to see kind of the magnitude of some of these forces. And then after this, we're going to do another example of someone that's injured their hip, where their hip abductors is not able to produce as much force as it is now, and we're going to see how that affects the forces and how that affects the motion. Okay. And so to kind of give you an idea, let's apply kind of a typical weight of a person's body. So let's assume that the weight of the person's body, WT, is 300 newtons. Rounded to kind of a nice kind of whole number here, so that we can just for comparison. Okay. So let's start solving the problem. So remember, our goal is to solve for FM and for J. Okay, so let's sum up the forces in X and Y directions. So we sum up the forces in the X direction. We only have two components here. Okay. And luckily for us, the angles that are given here, these angles are with respect to the horizontal. And so we don't have to add any angles or subtract any angles. So we can just take them as they are. So some of the forces in the X direction we have minus FM cosine of 70 degrees plus J cosine of 75 degrees. That's equal to 0. The weight doesn't imply any force in the X direction, because remember, the weight we always assume is kind of vertically downwards. And then we have the sum of the forces in the Y direction. And so in the Y direction, we have a minus FM sine 70 degrees plus J sine 5 degrees. Okay. So the signs in these equations here are given based on the directions of the arrows, or at least the way that we drew them. Okay. And then in the Y direction, we have to account for the weight. And so we have to say minus WT, and all of this is equal to 0. All right. We have two equations and two unknowns. All right, so we have a fairly simple system here. So there's not much to this. And so let's just kind of solve this very quickly. And so let's kind of solve this by substitution. So I'm going to take this first equation here and solve for FM. And so if we solve for FM, we add FM cosine 70 to both sides. We divide it by cosine 70. So we make this is equal to J cosine of 75 degrees divided by cosine of 70 degrees. Okay. And so let's take that and plug into this equation here. All right, so if we do that, we get minus. We're going to plug in for FM, so we get minus J cosine of 75 degrees. That's like cosine of 70 degrees. Sine degrees plus J sine 75 degrees minus WT is equal to 0. All right, and so we have just one equation here and one unknown, and so we can go ahead and just kind of work through this and solve for J. Okay. One thing I'll note is that we have sine of 70 over cosine of 70, and so this becomes tangent of 70 degrees. And so if we work through that algebra and we compute J, so that's going to involve the WT divided by a lot of trig terms. And so we get J is equal to 1177.3 newtons. Okay, so let's plug this back in and solve for FM. Okay, so we have our FM equation up there, so we just multiply by cosine 75 divided by cosine 70. What we get is FM is equal to 890, 81 newtons. All right. Fairly straightforward, right? And so we didn't even need a moment equation for this. Let's compare these forces to the weights, right? And so these numbers were computed assuming that the weight of the person was 300 newtons. And so when you compare the magnitudes of these forces compared to the weights, both of them are a lot higher, right? The muscle force is almost 3 times as much, and then the joint reaction force is almost 4 times as much. And of course, this isn't the whole picture. And so, just like we did in the upper extremity, we only consider just a single muscle, right? In reality, you have kind of multiple muscles in that area kind of all working together to kind of, help with the same thing. And so, you're not going to have just one muscle kind of exerting that much force, but this kind of gives you the an idea of just how much force and how much pressure is actually exerted inside inside the joints in your body. Okay. Okay. Double negative there. I guess it is common. And so when you're just kind of standing still or just kind of walking very leisurely, the forces at your hip joint, the joint reaction forces can be anywhere between 250 to 300% of your body weight. So that's not even doing anything. That's just standing there. Okay. And then under strenuous exercise, and so let's say that you're either jumping or you're sprinting or you're doing something kind of strenuous on your body, this can go up to anywhere between 400% to 850%. So it's pretty significant, and your hip there is a lot of this weight. All right, any questions on this? Okay. All right, so that's a healthy hip, and so that's a person with kind of a very healthy hip abductor and very healthy hip joint, obviously, to kind of bear all this. Next, let's look at someone that that has maybe an injured hip. And so under an injured hip, typically what happens is that the person's hip abductor muscles are not able to exert as much force as it needs to. And so remember we talked about, one of the main things that causes stress on your hip abductor muscles and your hip joints is the fact that when you walk, you kind of, shift your body weight so that it's right on top of your, right on top of your foot. Okay. And so people with an injured hip, they're not able to do this. And so what they find is that when you take a step, right, you're not able to kind of produce that kind of subtle shift in your body weight over. Right. And so to kind of help alleviate this, people with an injured hip or just kind of just trouble walking in general have to walk with a cane. Okay. And so we'll go with something like this. So we have kind of a leg. Okay. And so what you'll actually see, and actually kind of what's most comfortable for people, is for people to actually hold the cane on the opposite side on where their hip is injured. Okay. And so let's say that, let's kind of draw the hip abductor muscle just as we did before. Okay. So those are the muscles of your hip abductors. And so because of the cane or the presence of the cane on the opposite side, that kind of offloads some of that weight. So you don't have to kind of rotate your leg as much to kind of maintain balance. Okay. Let's consider a case like this. So let's say that we have 200 newtons being the amount of weight that's being offloaded to the foot. Okay. And then the cane is sharing the other part. So I don't know why I did this. I kind of wish I did so that the number added up to the same same as before. But let's say that this is a slightly lighter person. So we have 200 newtons on the foot, and then he's using the cane to support about 50 newtons of his weight. And so about 20% weight is being offloaded to the cane. All right, and so we're going to do the same thing here. And so we're going to compute the amount of muscle force and joint reaction force at the hip joint. The hip joint being the joint here. Our free body diagram for this one's actually going to be quite different because we have the cane kind of offloading some of that weight, but also we're actually going to consider some of the weight of the leg. Oh, that's why I did that. So the weight of the leg is going to make up the rest of the. All right. Any questions on this example so far? Okay. All right. So let's go ahead and start with our free body diagram of the leg. Let me draw really big here just because there's going to be a lot going on. Okay. I'm going to exaggerate the tilt a little bit just to just to make it a little bit easier to draw. But because of the cane, your leg isn't actually tilting so much. All right, so we're doing the entire leg here. So we're assuming the leg is kind of one big step. All right, so halfway up this leg, we're going to have the knee. And so we're going to assume that our leg has its own weight that is acting at the knee. Call this weight of the leg. We also have the weight of the entire upper body. Of course, we haven't drawn the upper body in this case, but the way that we're going to express the weight of the upper body is through a normal force on the bottom. So this 200 Newton force here represents the weight of the upper body. And the other forces that we have here are going to be the muscle force. And so we have Fm. And so that's the muscle force from our hip abductor muscles. And then we have the joint reaction forces at the hip joint. So the hip joint is this kind of appendage that I've kind of drawn off to the right here. That means the joint reaction forces are going to be here. So we have a Y in this direction. And let me draw this as well. Let me go ahead and draw the kind of vertical line here. And so that vertical line is going to represent kind of the position of the hip joint. Okay. And what we're going to do is we're going to define everything kind of relative to that joint. Okay. And I think I did it this way just to make it convenient to compute the moments. Okay. All right, so the first distance that we're going to compute, we're going to label here is the horizontal distance between where the normal force acts and the hip joint. And so we'll call this LF. Next, we have the horizontal distance between the knee and the hip joint. We'll call this LL or L leg. Okay. So that's the moment arm for the weight of the leg. we'll put this distance, and so in this case, the muscle attachment distance is given in terms of that horizontal distance. So everything is all the distances are defined in terms of the in terms of where the horizontal distance is relative to the hip joint. Okay. So we'll call this LM. Another distance that we need in this problem is we need that vertical distance. Okay. And so unlike the previous problems where the muscle force is defined kind of in the same kind of horizontal plane or horizontal line as the joint, here we're kind of offset a little bit because of the femoral head, right? And so not only do we need that horizontal distance, we need the vertical distance as well. Okay. And so this vertical distance I'll call EGME. All right, and the last piece of information that we'll have here is the angle for the FM. Okay, and so remember we're almost always given the attachment angle for the muscle force. And so this angle here is going to be 70 degrees. And I want to make kind of one important distinction here. So that 70 degrees, if you'll notice, I kind of drew that horizontal line there. That 70 degrees is defined relative to the export, so the pure horizontal. It's not defined relative to the line of the hip joint, which is I think a lot of people look at this problem, it typically is, but in this case it's defined relative. Okay. All right, so there's a lot going on in this ray body diagram, and so whenever you're doing these problems, you always need to kind of pay attention to, or really kind of take into account where all the distances are and everything, and draw it really carefully, because if you don't kind of draw a figure like this, it's very kind of easy to kind of get lost and very easy to kind of misplace things or give things the wrong side. Okay, so let me give you some numbers for all of these. So we have all these distances here, and we have HM as well. So we'll assume HM is just 1 centimeter. We'll assume LM is 7 centimeters. L leg is 6.5 centimeters. LF is 5 centimeters. And the weight of the leg we'll assume is 50 inches. All right, so those are the numbers that we're working with. All right, any questions on this? Okay. All right, so let's go ahead and start solving. And so we've taken a lot of care to make sure everything is accounted for in this problem. So let's go ahead and all right, so just like before, we're going to start with the sum of the forces. We have some of the forces in the x direction. Most of the forces that we have here are purely vertical. So the weight of the leg and the normal force of the ground are purely vertical forces. So we can just sum up just the muscle force. And so we have FM. FM cosine of the angle, which is 70 degrees, plus JX is equal to 0. And then we have some of the forces in the y direction. We have FM sine of 70 plus JY minus the weight of the leg, and then plus the 200 newtons from the ground. All that is equal to 0. Okay. So we need one more equation, right? So because we have not only the muscle force, but we have both components of the reaction force, so Jx and Jy, and so we need the moment equation to kind of complete the system. Okay. But we have to be really careful here. And so, you know, the way this problem is defined in terms of the distances and the angles is a little bit strange, right? And so, so you want to be kind of really careful with how you account for all the different components, right? And so to compute the moment equation, we have to take into account both the horizontal and vertical components of FM and make sure those make it into the moment equation. Okay? So this is a little bit strange. So this is kind of a different approach than what we did last week in terms of the moments. Just because of the way the moment, just because of the way the muscle forces were defined. But here we have to be kind of a little bit more careful. And so to kind of illustrate this, I'm gonna kind of draw you a figure. And so let's say that this dot right here is the hip joint. We're going to ignore Jx and Jy for now, just because we know for sure that Jx and Jy don't contribute to the moment. Okay. And then FM is acting kind of like. All right. And so in terms of what's given to us, we know this distance, and we know this distance, okay? And so we know this distance right here is LM. This distance right here is HM. Okay. Let me break up FM into its two x and y components as well, because we know for sure this angle right here is 70 degrees, right? And so if that angle right there is 70 degrees, we can break this up into FM y, okay? And then FM x. FM y is FM sine of 70. FM x is FM cosine of 70. And so the way that this problem here is drawn, both FMX and FMY are going to contribute to the moment, right? And so if we take this FMY vector, and so we kind of make sure that it kind of starts in the same spot, okay? If we draw the moment arm, or kind of the perpendicular distance between the vector and the joint, right? It looks just like this. And we know that distance is LM. And so on the one hand, we're going to have one component of the of the moment be FMY times LM. But then in this case, FMX is gonna contribute to the moment as well, because it doesn't point directly at the joint. Okay. And so I think this is the part that's a little bit different than our previous examples, where if when we took the parallel component or the X component, in our previous example was that component pointed directly at the joint, and so it didn't contribute anything to the moment. And so in this case, we actually do have something. Okay. So I kind of extend this out just like this. Okay. Then what we have is this vertical distance here called HM, right? So that's how we define it. And so the other component of the moment is going to be FMX multiplied by HM. Okay. But both of these terms here are going to contribute to that. All right, any questions on that? Does that kind of make sense while we take into account both components? All right, and so all that's left to do now is to kind of decide what signs we're going to choose for these components here. Okay, so FMY, if we kind of look relative to the hip joint, FMY is gonna want to try to rotate it clockwise, right? And so FMY is going to have a minus sign, okay? Where FMX is actually going to try to rotate it the opposite way. So FMX is going to try to rotate that. So FMX is going to have a positive sign. Okay, and so if we bring all this information together, while remembering that the weight of the leg and also the normal force from the ground at 200 newtons are also going to contribute to the moment. And luckily, the way that we define the lengths, their moment contributions are actually quite simple. Okay. And so when we sum up the moments around the hip joint, what we get from this is, let's start with the contributions from the muscle force. We have minus FM. Remember, FMY is FM sine theta. So F minus FM sine 7 degrees multiplied by LM plus FM cosine 7 degrees times HM. We have the weight of the leg, and so the weight of the leg, let's kind of check back on the direction for that. And so the way we drew it here, weight of the leg is on the right side. And so if we're going to go downwards, this is going to be a clockwise moment. And so we have minus W leg times L leg. And then finally, we have the 200 Newton ground force. And so we have plus 200 Newtons multiplied by LF. And I kind of spoiled it there, but the 200 Newtons is going to be a counterclockwise because it's an upward force to the right of the joint. And so that's going to cause a counterclockwise. All right. So lots of free body diagrams and much algebra later. We have arrived at this equation here. Okay. And the good thing about this equation, okay, as is usually the case in our moment equations, is that we only have just a single unknown. So our only unknown here is FM. Okay. And so let's solve this equation for FM. And so, if you want to check the details of the algebra, that is in the notes. And so what we get from this is 212.48 newtons. Right, so what we have, and so if you compare this to our first example that we did today, this is obviously a very huge reduction. And then now that we have that now that we have that number for FM, we can go ahead and back plug this in for JX and JY. Okay. And so again, just for the sake of time, I'll leave those details to you, or you can kind of double check them in the notes. But JX in this case is going to be 72.67 newtons. Y is has a magnitude of 350. In fact, I think relative to how we drew them, this is going to be a negative 72 and negative 52. Okay. All right. So now that we have the components for JX and JY, we can go ahead and compute its magnitude. And so the magnitude of the joint reaction force J is going to be square root JX squared plus JY squared. Okay. And so we plug those in and we get magnitude of 357.46. And so you can see that compared to our first example here, this also resulted in a very large reduction in joint reactions. Okay, and if you look at kind of what changed for this problem, obviously the geometry that we did here was a lot different. But when you compare it to the first problem, the main thing that changed is kind of where the weights were kind of positioned relative to each other. Okay? And so because we kind of straightened the leg a little bit, that kind of helped alleviate a lot of the pressure. Okay. And so people think that when you have a cane, you think that people are leaning on the cane. The reason it's easier is because you're offloading a lot of the weight. But you can see in this case, we didn't actually offload that much weight to the cane. So compared to our original 300 newtons of weight, we only offloaded 50 newtons of weight to that cane. Okay. The bigger benefit that you gained here was just in kind of the kind of where your center of mass is located, and just kind of offloading. Not exactly the weight, but there's less work for the hip abductors to do because your leg kind of isn't in as compromising a position as it was before. Okay. All right. Any final questions on this example here? Okay. All right. So that's all we got time for today. We have 3 minutes left, but I'm not going to start the day. And so when we come back on Wednesday, we'll do an example with the knee. And then we'll do an example with the ankle. And then we'll talk about injury. All right, but thank you guys for coming today. I hope you guys enjoy the rest of your day. I will see you all on Wednesday.
Hey, Professor.
Hey, how's it going?
It's going good. I'm good. I'm going to be doing a CFD on ANSYS. So
Okay, yeah, I don't, yeah,
Okay,
yeah, let's have a time to talk about it. who are you doing the project?
Oh, thanks.
Okay, yeah, definitely happy to help. Yeah, I'll email you back my schedule and then let's find a time. Let's talk.
Okay, cool. I was just in the area, so I figured if you didn't check your email.
I saw it like kind of right as I was coming to class, like, all right, I'll email Tyler back when I get back to my office.
All right, no worries. Thank you, Professor Tran.
No problem. All right. Well, any final questions before I wrap it up? See you Wednesday.